My dear students of Standard 11, welcome back to your Chemistry 1 class. Dear students, we are talking about the configuration of electrons in different shell and subshell of an atom. Last class, we learned three principles by following which the electrons are arranged. The principles are Pauli's exclusion principle, Hund's rule, and Aufbau principle. Today, we will learn about the electronic configuration and also we will learn how the electrons are configured in different orbit and orbitals. So today our topic is electronic configuration. Now, before going to our main topic, just 1 minute I want to review the previous class. That is electronic configuration. All you know what is electronic configuration. Electronic configuration is the arrangement of electrons in different orbitals of an atom. Now, this electronic configuration is done by following three main principles. These are Pauli's exclusion principle that tells that any two electrons of an atom will have four different quantum number. That means the value of four quantum numbers are not identical. At least one quantum number must be different. Another one is Hund's rule. Hund's rule is what? Hund's rule tells that when electron goes to any degenerate orbitals, then at first the degenerate orbitals are filled up by one electron, and after filling up by one electron, then the rest electron will make pair in these degenerate orbitals. And when the electrons are gone by one in each degenerate orbitals, then they will go to in same direction, and the second electron will go in opposite direction. And another one is Aufbau principle, the most important principle. It tells that electrons will go to different orbitals according to their increasing energy levels. That means at first electron will go to lower energy orbital, fulfill it, then it will go to higher energy orbital. Now we will see some electronic configuration. So, how the electronic configuration is written or rules of writing electronic configuration. To write electronic configuration, Aufbau principle is most followed. Almost all these three principles, Aufbau principle is the most important one to configure the electrons. So here, by following Aufbau principle, electronic configuration of some elements are shown. Here, the electronic configuration of any element can be written by following the Aufbau principle. For example, the electronic configuration of iron can be written as follows. Look, to configure the electrons of an atom having bigger atomic number, you should memorize the energy serial of orbitals, or you can draw this energy serial and from there you can write the serial of different orbitals according to their energy. So look, when you will write the electronic configuration of any atom, iron, its atomic number is 26. That means it has 26 electrons. So, at first, the electron will go to lower energy level, fulfills it, then they will go to higher energy level. Here, 1s is filled up by 2 electrons, then 2s is filled up by 2 electrons, 2p by 6 electrons, 3s by 2 electrons, 3p by 6 electrons, 4s by 2 electrons, and then the rest of the electrons will go to 3d orbital. Here in 3d orbital there are 6 electrons. Now look here, the electronic configuration is written according to their increasing energy level, but this is not correct form of electronic configuration. When you will write the electronic configuration, then you have to follow the energy level. That means first energy level 1s, second energy level 2s 2p, third energy level 3s 3p. There is 3d, so 3d will be written here. So the electronic configuration should be written as 1s2 2s2 2p6 3s2 3p6 3d6 4s2. This is the correct electronic configuration of iron. Dear students, all you learned this electronic configuration in previous class. Now, when you want to write the electrons in different shell, then just you will count all the electrons from any shell and you can write. Here in first shell there are 2 electrons. In second shell there are 2 and 6, total 8 electrons. In third shell there are 6 to 8 and 6, total 14 electrons, and in fourth shell there are 2 electrons. So in this way also you can write the electronic configuration. In junior class you had learned this type of electronic configuration, but from there you cannot find out the electrons present in different orbital. Only the electrons present in different shell can be understood from there. Now, another way to write the electronic configuration. It is maybe new for you. Now look, in periodic table, every period ends at inert gas. You know this. In first period, helium is the last element. Second period, neon. Third period, argon. Fourth period, krypton. Fifth period, xenon. In this way. Now, can you tell this inert gas has how many electrons on its last shell? You know this, that in every inert gas there are total 8 electrons on their last shell except helium. That means neon has 8 electrons on its second shell. That means the last shell electronic configuration of neon is 2s2 2p6. In this way, argon has also 8 electrons. So the electronic configuration of argon is 3s2 3p6. In this way, krypton it is 4s2 4p6. Then xenon, that is 5s2 5p6, and so on. So look here, for iron the last p orbital is here in third shell 3s2 3p6. So up to this is the electronic configuration of argon. So we can write the electronic configuration of iron in this way. Up to this is argon, so it will be in third bracket, and then the rest of the electrons they are in 3d6 4s2. This is also the way to write up electronic configuration. Now, by following the Hund's rule, you can write the electronic configuration like argon and then 3d6 4s2. In 3d orbital there are 6 electrons, so at first everyone will fill up by 1 electron in same direction, then the second electron will come to the first d orbital in opposite direction, and 4s2 there are 2 electrons in 2 opposite direction. This is also a way to write electronic configuration. Now dear students, we have learned many ways to write electronic configuration. You can use any way, but not this. It is needed only when you will make bond or when you will make any ion from atom. Now we will learn the electronic configuration of any ion. Now dear students, we have learned the electronic configuration of iron. So from there we can write the electronic configuration of ferrous and ferric ion also. This is the electronic configuration of iron. Now, you know, positive ion is formed by releasing electron. Iron, when it releases 2 electrons, then it will form ferrous ion, and when it releases 3 electrons, then it will form ferric ion. Now, what do you think? An atom will release electron, but from where? From where the last electron comes, or from the last shell? Most of the time you are doing wrong, that you think that the electrons will be released from the shell or from the orbital where it comes at last. That means from this 3d6. But no, the electrons are released from the last shell of the atom. Here iron, it has 4 shells, and in last shell there are 2 electrons. So when ferrous will form by releasing 2 electrons, then these 2 electrons are released from 4s orbital. So the electronic configuration of Ap2 plus will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, because these 2 electrons are released to form Ap2 plus. It can be also written as up to 3p6. This is the electronic configuration of argon, then 3d6. And by following Hund's rule, the configuration can be written as argon 3d6. Now look, this is the electronic configuration of ferrous when 2 electrons are released. In the last shell of iron, there are 2 electrons. So these 2 electrons can be easily released from there. Now, when ferric will form Ap3 plus, then how many electrons will be released from iron? 3 electrons. 2 electrons will be released from 4s orbital, and another 1 electron. Yes, now this 1 electron will be released from this 3d orbital. So the electronic configuration of ferric will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Now it can be written as after this argon and then 3d5. By following the Hund's rule, the configuration can be written as argon, and then in d orbital there are 5 electrons in same direction. These are the electronic configuration of 2 ions, ferrous and ferric. Now dear students, can you tell which ion is more stable, ferrous or ferric? You know, ferrous and ferric both are stable ion, and there are many compounds of ferrous and ferric. Ferrous chloride, ferric chloride, ferrous sulfate, ferric sulfate, ferrous nitrate, ferric nitrate. There are huge compounds of both ions. But here, which ion is more stable comparatively? How can you understand this? You know that degenerate orbitals get more stability when they are half-filled or full-filled. That means the electronic configuration of ferrous, that is 3d6. This d orbital is neither half-filled nor full-filled. And when you will write the electronic configuration by using Hund's rule, by following Hund's rule, then you will see that in d orbital there are 5 electrons are in same direction, but 1 orbital it is in paired condition and in opposite direction. But if you see the electronic configuration of ferric, then the last shell, the degenerate orbital 3d, it has 5 electrons. That means it is half-filled condition. 3d5, it is half-filled condition, and if you see the electronic configuration by following Hund's rule, then you will see that all electrons are present in same direction. Here no orbital is empty or no orbital has more than 1 electron. So this is comparatively stable configuration than this one. So from these 2 electronic configuration, according to their electronic configuration, we can tell that ferric ion is more stable than ferrous ion. Now we will see another electronic configuration, comparatively bigger atomic number. So we need this energy serial. If you don't memorize it, then it is tin. The atomic number of tin is 50. That means tin has 50 electrons. So these 50 electrons are configured in this way. Look here, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2, because up to 4d10 there are 48 electrons, and then the rest 2 electrons will come to 5p orbital and it will be 5p2. So this is very easy to write the electronic configuration if you can memorize this energy serial. Now here also look, here the orbitals are arranged according to their increasing energy level, not in energy shell. So here also you will arrange this. Here after 3p6, here will come 3d10, 4s2, 4p6, 4d10 will come here, and then 5s2, 5p2. So the correct electronic configuration of tin will be this. Here from there also you can write the electrons present in different shell. Here in first shell there are 2 electrons. In second shell there are 8 electrons. In third shell there are 6 to 8 and 10, total 18 electrons. In fourth shell there are also 18 electrons, and in fifth shell there are 4 electrons. So this is also the electronic configuration by showing the number of electrons in different shell. Here also you can write the electronic configuration by using inert gas. Look here, the electronic configuration up to this 4p6, here 5p is not filled by 6 electrons. So the inert gas will not come here. Here up to 4p6, the fourth inert gas, helium, neon, argon, krypton. The fourth inert gas is the inert gas present in fourth period is krypton. So up to this is krypton, and then 4d10, 5s2, 5p2. This is also the electronic configuration of tin. Now, by following the Hund's rule, the electronic configuration can be written as krypton and then 4d10. So 4d orbital, there are total 10 electrons and they are in paired condition with opposite direction. 5s2 also like this, and 5p2. In 5p orbital, there are total 3 orbitals, but there are 2 electrons. So these 2 electrons will go to 5px and 5py in upward direction. This is the electronic configuration of tin by following Hund's rule. So dear students, today we have learned the electronic configuration of any atom by following above principle and also by following Hund's rule in different way also. And also we have learned the electronic configuration of any ion. So dear students, today after this, in next class I will come with some deviation of electronic configuration from the general rules. So today up to this, thank you everyone. Goodbye to all.